the Bohr model of the atom. We have seen how the model of atoms has been modified from the Greeks to Dalton and then to Rutherford's nuclear model. An atom has protons and neutrons in the nucleus. These particles carry essentially all of the mass, and tiny electrons on the outside. Rutherford also found that atoms are mostly empty space. In order to understand the next step in the development of the modern model of the atom, we need to take a short side trip to talk about light waves and energy. If you pass white light through a prism, it breaks into the colors of the visible spectrum. Each color has a different wavelength, as shown in the scale along the bottom of this picture. Here, shorter wavelengths are on the left, and longer wavelengths are to the right. This only shows the visible spectrum. Shorter than 350 nanometers would be ultraviolet radiation, and then gamma rays. And to the right of 750, red, would be infrared and radio waves. Light is made up of waves. There are several measurable characteristics of waves, of which we are interested in 3. Wavelength, the distance from one peak to the next. The symbol for this is the Greek letter lambda. Velocity, or speed, how fast the wave is moving, symbolized by v, or, in the case of light, c, the symbol for the speed of light. And frequency, which is how often a peak passes any given point, symbolized by the Greek letter nu, which unfortunately in this font looks like a letter V. If you think about a wave moving at a constant velocity, how often a peak passes a certain point will depend on the wavelength. A longer wavelength will have a smaller frequency. Fewer peaks will pass in a given time than if the wavelengths were shorter. So frequency equals the velocity divided by the wavelength, or nu equals c over lambda. It turns out that the energy of a wave is directly proportional to the frequency. Energy equals a proportionality constant times frequency. That constant is called Planck's constant, named for Max Planck, who figured it out, and its symbol is H. So energy, E, equals h nu, but nu equals c over lambda. So energy equals h c over lambda. This means that as the wavelength increases, energy decreases. So if we go back to our visible spectrum, we can see that red light has less energy than blue or violet light. It has a longer wavelength, and so a lower frequency and a lower energy. So what does this have to do with atomic structure? Recall the line spectra that you saw in the lab. Niels Bohr saw these line spectra by allowing the light given off by specific elements when electricity was run through them to pass through a prism or a diffraction grating. Rather than seeing the continuous spectrum, he saw discrete lines of different colors. Each lines he saw were characteristic of the element being energized. Bohr Bohr, of course, was familiar with cathode ray tubes, and he knew that the rays being given off were electrons. Something about these energized electrons caused only specific wavelengths, and therefore specific energies, to be given off. Bohr's conclusion was that the energy of the electrons was quantized. Electrons could only have specific amounts of energy. He proposed that the electrons of an atom could only be found in specific energy levels, or shells, and not at any of the energies in between. It's like the difference between walking straight up the hill to the dining hall or taking the stairs. The stairs are quantized. You can't step in between. Bohr explained line spectra as electrons absorbing the energy of the electric current and jumping up to a higher energy level. As the electrons drop back down, they emit that extra energy, which is given off as a photon of light at a specific wavelength, depending upon how many levels the electron is dropping and which level it is dropping from. The energy to drop from level 3 to level 2 is less than the energy to drop from level 3 to level 1. And the energy difference between each level is unique also. 3 to 2 is different from 2 to 1. This accounts for the line spectra observed by Bohr, and you. Bohr also calculated the number of electrons that can fit in each energy level. The lower levels, closer to the nucleus, are smaller and so can hold fewer electrons. The farther out you go, the more electrons will fit in the available space. So the maximum number of electrons in an energy level is 2n squared, where n is the level number. So level 1 can hold 2 electrons. N is 1. N squared is also 1. 2 times 1 is 2. Level 2 can hold 8 electrons. 2 squared is 4. 4 times 2 is 8, and it goes up from there. So, as atoms get bigger, with more protons, and so more electrons, those electrons go into specific energy levels, filling the lowest level first, then the second level, the third, etc.